So we're going to start today by kind of rehashing a little bit of what we saw at the end of Friday. And the reason we're rehashing it is I went through this last section very quickly, and we might have dropped a couple of concepts along the way that I wanted to make sure that we understood more fully. So we ended on Friday largely looking at the duality of light. Light being as a participant in a wave form, as well as in a particle form, in terms of photons being these packets of light energy that are capable of, because of their energy, displacing physical objects from other physical objects. And so that was the photoelectric effect. The idea that light could pack an energy punch great enough to take an electron and shoot it out of a metal sample. Well, the flip side of that argument is, well, if light can exist as this wave and as this particle, can matter, which we usually think of as particulate, also have wave characteristics? And Louis de Broglie says, sure, why not? And he actually derives an equation to equate these ideas. And I'm not giving you the equation here. I'm actually going to show you a really short video that kind of ties all of this together. That is going to show you the equations. The reason I'm not showing you the equations now is because we're not going to use them. We're really talking about this just on a conceptual kind of basis. And the reason I'm going to kick it to a video here is because the video is going to be able to show what I can only describe, and it's going to do a better job. And so I'm not afraid to admit that. What we need to understand about the Broglie wavelengths, though, is that all objects in motion do exist and have a wave-like property. So a person moving around a room, an object being thrown through the air, does have wave-like properties. However, according to the de Broglie equation, those wave-like properties are so small that they're practically non-existent. We treat them as non-existent, as negligible. But if we get down to the microscopic world, those wavelengths associated with those tiny little objects suddenly become significant. And to further explain that, I'm going to kick it over to this video. This is from Professor Dave Explains, and we're not going to watch the whole thing. We're only going to watch maybe the first 2.5 minutes of this. The remaining 4 minutes go way deeper into calculus and physics than we care to. But I want you to pay attention to these first 2.5 minutes, because what it's going to do is it's going to kind of contextualize what we were talking about with the Bohr model, what this de Broglie introduces as far as wave properties of matter, and how we merge them together to give us the quantum mechanical version of the atom that can kind of explain both worlds and why the Bohr model works, just not in the way that we thought originally. So let's listen in.
Professor Dave again. Let's take a look at the Schrodinger equation. Work of Planck and Einstein, we were forced to accept that energy is quantized,
and that light exhibits wave-particle duality. Then de Broglie extended this duality to include matter as well, meaning that all matter has a wavelength, from a tiny electron to your whole body to a massive star. However, an object's wavelength is inversely proportional to its mass. So objects bigger than a molecule have a wavelength that is so tiny that it is completely negligible. But an electron is incredibly small, so small that its wavelength is indeed relevant, being around the size of an atom. So we must view electrons as both particles and waves from now on. Therefore, we must discuss the wave nature of the electron. So what kind of wave might this be? We can regard an electron in an atom as a standing wave, just like the kind we learned about in classical physics, except that rather than something like a plucked guitar string, an electron is a circular standing wave surrounding the nucleus. If we understand this, it becomes immediately apparent why quantization of energy applies to the electron, because any circular standing wave must have an integer number of wavelengths in order to exist. Given that an increasing number of wavelengths...
So I'm going to just interrupt here for a second. So with this kind of in mind, now we can start to see some of why these energy levels exist and how they have different energies associated with them. So remember, energy is Planck's constant times the frequency. Would you agree that this version of the atom, because it's got 10 wavelengths in a more compacted space, has a higher frequency than an atom that has one wavelength in the same amount of space? That's why it is the way that it is. That's why this energy level with the 10 wavelengths in it is higher in energy than the wavelength, the first energy level that only has the one wavelength in it. That's why the energy gap between here and those other ones is a very set amount of energy. It can't exist in the in-between states because I've got to complete the circle. If I have that wave and it doesn't complete the wave on the other side as it finishes the circle, then it's not going to be an allowed state. It doesn't have the right frequency. So those individual energy levels have to exist at these very specific frequency values. Go outside of those frequencies, the wave doesn't complete. We have an improper energy level.
Means more energy carried by the wave, we can see the Bohr model for the hydrogen atom begin to emerge as we imagine a standing wave with one wavelength, and then two, and then three, and so forth. This is the reason that an electron in an atom can only inhabit a discrete set of energy levels. The circular standing wave that represents the electron can only have an integer number of wavelengths. When an electron is struck by a photon of a particular energy, this energy is absorbed, promoting the electron to a higher energy state and increasing the number of wavelengths contained within the standing wave. This is why the electron goes to inhabit a higher energy level, and this is what is fundamentally occurring during electron excitation. Furthermore, it is...
So we'll stop at that because this actually gets into bonding, and we're not going to talk about bonding for a little bit here. So we can start to put together, based upon these ideas of thinking about the electrons as in these circular standing waves, thinking about it in terms of that Bohr model, we can start to really get an idea of the picture of the energetics of the electrons in that atom. What we still have a hard time with, however, is we're not incredibly good at trying to figure out where the electron is. So even if we know that it's in the third energy level, all that tells us is that we know the frequency of that wave, because we know the energy of that energy level, but it really doesn't tell us anything about where that electron is going or what it's doing. And there's a reason for that. It's called the Heisenberg uncertainty principle. The Heisenberg uncertainty principle tells us that there's a relationship between how much knowledge we have of where an electron is and how much we can talk about its momentum, where it's going. And the very reason we have such difficulty with this is when we go to observe electrons, we're inherently going to bump them from their current position. I go to observe an electron by doing photon analysis on it. I shoot photons at the electrons to try to determine their location. Well, the problem is, as soon as that photon hits that electron, it bumps it off of its current course. And we don't know to where it's been bumped. We don't know how much of the electron, how much energy that electron has absorbed, whether it's been promoted to a higher energy level or if it's just been knocked off of its path, like two pool balls hitting each other on a pool table. We don't know. Now, the Heisenberg uncertainty principle tries to give us a quantification of this kind of relationship. And the Heisenberg uncertainty principle in terms, mathematical terms, is this. Delta X, that is the degree to which we know the position of an electron, multiplied by delta P, the degree to which we know the momentum, the direction of the movement of an electron, will always be greater than or equal to Planck's constant divided by 4 pi. Now again, don't get bogged down in the details here. We're not going to actually do any calculations of the uncertainty principle here. But what I want you to know is this is a constant value. H is a constant, 6.626 times 10 to the negative 34th joule seconds. 4 is a number, and pi is a number. So the right-hand side of this equation is a fixed value. The left-hand side of this equation is not. But it does tell us that if I know this, if my error bar on position is small, my error bar on the momentum is going to have to be large to account for that. Because that left-hand side of the equation is always bigger or equal to the right-hand side. This is a property called complementarity. The more I know about one, the less I'm going to know about the other. And so this presents some problems to us when we're trying to figure out where an electron is or trying to predict electronic behavior and trying to know any of it with a great degree of precision. So just to summarize here, kind of looking at what we've been doing the past couple of days. The photoelectric effect gave us information, told us that light had dualistic characteristics. Light could exist not only as wave, but also as particle. Those particles of light we call photons. De Broglie flipped it around, said that there must be a duality to particles as well, and that they can have wave characteristics based upon their size. The bigger they are, the less we care about their wave properties. The smaller they are, the more their wave properties stand out. And this led us to a final version of the Bohr model of the atom, where we talk about those circular standing waves representing those energy levels, as opposed to linear waves that we were thinking about when we were looking at light. The uncertainty principle kind of puts the one last piece in there that says, okay, even with all of that information, the Bohr model still has an issue because we can't really know where the electron is going and where it is at the same time. Now, seeking to try to aid and help with this, we turn our attention to Erwin Schrodinger. Erwin Schrodinger creates the Schrodinger equation. And again, this is an equation, this is a differential equation. When you actually break H and E out into mathematical terms, you end up getting a whole bunch of calculus as a result. We're not going to focus on the calculus. We're not even going to focus on the math here at all. We're just talking about the results. And the results of this equation allow us to take into consideration that wave-particle duality of the electron and produce for us something called the wave function. The wave function is given to us here. By this capital Greek letter psi. Psi is the wave function. It is the result of the Schrodinger equation that helps to put into mathematical terms what the wave-particle duality of the electron looks like. And the net result of this wave-particle duality is a graph, a sine wave. This is an example of a wave function. Tells us how the electron wave is interacting in space. Now, I don't know about you, but if I look at this, I go, I don't see an electron there. What does this graph tell me anything about what an electron does or what it's going to do, where it's going, where it is, any of that stuff? And the answer to that question is, it really doesn't. But here's something that does. If we take this wave function and we square it, it turns it from a wave to something called a probability density map. That probability density map is something that we can use. Because what it's going to tell us is where is the electron most likely to be found. So instead of thinking about a wave electron, we start to think about electrons as being contained in these three-dimensional objects. And so that's how we can get around the Heisenberg uncertainty principle. Because Heisenberg's uncertainty principle says, well, the more we know about the precise location of an electron, the less we can know about its momentum. Well, I say, okay, well, let's forget about the knowing the exact position. Let's just say that it's in this general area. If we know what general area it is in, it can give us some idea about what kind of energy it has. Now, credit for this reinterpreting of the wave function by squaring it is attributed to Max Born. Max Born proposes that the square of the wave function here ultimately decides what an orbital looks like and gives us this three-dimensional probability map that tells us where we are most likely to find an electron at a given energy in a given energy level. And the result of these squares are what we call atomic orbitals. So if you go back to your previous understanding, your previous work in chemistry, you probably heard at least a little bit of something about atomic orbitals in terms of knowing that these orbitals, these shapes, are where we find electrons inside of the atom. Now, we're going to break it down a lot further than that today, but you probably at least saw this in some kind of way in the past. So Atomic orbitals are three-dimensional shapes. They are graphical representations of that Schrodinger equation. The shape of the orbital has a lot to do with the energy that is contained in them. Some shapes are low energy, some shapes are high energy. The low energy shapes are the ones we see more often because electrons tend to occupy the lowest energy states possible. Remember, you defined ground state in your homework last night. Ground state being that lowest possible energy state. Electrons want to be in a low energy state whenever possible. They only go up to higher energy states when they've been excited in some kind of way through the use of a photon energy excitation or heat or something along those lines. The important thing to know about orbitals, though, they represent the most likely locations of the electrons. They don't represent the exact location in any kind of way. So again, this is kind of our workaround. This is our cheat to deal with the Heisenberg's uncertainty principle. Because we're not focused on where it is exactly, we're focusing on this general area where we might find it. And we know that with this general area is going to come a general energy associated with it as well. And so we can kind of know each one of those two items in the uncertainty principle with enough accuracy to be satisfied and not being hyper-focused on either one. So let's take a look at the different types of orbitals. So s orbitals. Things to know about the s orbital. S orbitals are the lowest energy orbitals. They are found in every energy level. And they are spherical. So when we start to describe orbitals, what we will usually describe in those orbitals are two things. We will describe first their energy level. And so when we look at the 1 and the 2 and the 3 here, that is referring to the energy level for that particular orbital. So 1, first energy level, 2, second energy level, 3, third energy level. And then there will be a letter to describe the orbital shape. So S refers to an orbital shape that is spherical. One other note about these, you'll notice these are probability density graphs here. So what they tell us is how likely is it to find an electron at these different ranges of distances from the nucleus. And so these distances here are in picometers. What's really interesting is, first of all, we should notice that as our energy level increases, the likelihood of finding an electron further from the nucleus also increases, which shouldn't come as a surprise. If it's at higher energy, it can push away further from that nucleus base. The second thing is that you'll notice that in these second and third energy levels, there are actually positions where there is no chance of finding an electron. So in the 2s orbital, just after 100 picometers, there is zero chance of finding an electron at that specific distance. At 100, and I'd say about 380 picometers in the 3s, there is no chance of finding an electron at those distances. Those are called nodes. And nodes are places where there's a 0% chance of finding an electron there. Now, the reason for nodes, it's kind of a long laundry list of reasons why they exist. But the important thing is that they do exist. And what we should notice is that as our energy increases, the number of nodes increases as well. And so not only do we see nodes increasing with energy level, what we'll also see is that nodes increase with complexity of the orbitals as well. So as we go from the s orbitals here, which are spherical, to the p orbitals that are dumbbell shaped, we'll notice that the number of nodes that exist increases as well. So let's take a look at that next shape then. P orbitals. P orbitals are dumbbell shaped. And only exist in the second energy level and above. Now, in total, there are 3 different p orbitals: the px, the py, and the pz. Now, one thing to also notice with the px, the y, and the z, those orbitals are arranged on the cardinal axis. So the p sub x is on the x-axis. The p sub y is on the y-axis. The p sub z is on the z-axis. And the reason I'm making this distinction is when we get to the next set of orbitals, that's not going to be the case for every one of them. So we want to distinguish some differences here. But those are the p orbitals, dumbbell shaped. They only exist in the second energy level and above. They naturally have a node in the middle of them. So those 2 lobes of the dumbbell are not actually touching each other. There is a natural node that exists at that origin point where the nucleus is. The last set that we're going to look at in high detail are the d orbitals. D orbitals are clover shaped and exist primarily in the third energy level and above. And one thing that we want to notice with them is that the system with which we specify which orbital is which changes. These 3, the dxy, the dxz, and the dyz, these ones have lobes that are between the axes. So the dxy, for example, it isn't on the x and y axis, it's between the x and y axis. You also notice that there are some natural nodes that exist between them. None of these orbital lobes are actually touching each other. So there are some certain distances, some certain spaces between that the electrons cannot be in and will not be in. The orbitals that have squared terms are on axes. So the dx squared minus y squared, those ones are directly on the x and y axes. The dz squared, the dumbbell lobes are on the z-axis. That donut ring is actually in the xy plane. Now, where did all of these come from? How did we come up with each of these different orbital shapes and notations and all of this? Well, these all come back to and are driven by something called quantum numbers. So we kind of worked this in reverse. Usually you want to talk about quantum numbers because quantum numbers dictate the shapes, dictate the number of orbitals that are there. But I wanted to kind of reverse it here because it's easier to kind of have a framework of what this looks like and then try to describe what made these in the first place. So quantum numbers. Quantum numbers are a series of 4 related numbers that specify a lot of information about electrons inside of atoms. And they start from very generic information about atoms and their electrons, all the way to specific information about a given single electron in an atom. We're going to start with the broadest. The broadest category is the principal quantum number. The principal quantum number describes what we will either call the energy level or we will sometimes refer to as the energy shell. Now, why do we use the term shell instead of level? 3-dimensionality. A shell reminds us that these energy levels are 3-dimensional, that they are consuming a 3-dimensional space. Whereas energy level, we can kind of get caught in that planetary Bohr model, which makes us think about that arrangement as being 2-dimensional only. What is the principal quantum number? Well, again, we're talking about energy, we're talking about size. These are positive integers, otherwise known as whole numbers. Starting at 1. And going basically until we get to the last boundary of the atom. So remember, one of the things that we talked about on Friday, the idea of n equals infinity. Infinity would be that mark, wherever it is, that defines the outer boundary of the atom. When we go past n equals infinity, we no longer think of the electrons being part of the atom, we think of the electrons being outside of the atom. For the most part, our whole numbers are going to be relatively small, 1, 2, 3, 4, 5, 6, 7, and so on. Especially when we talk about things in the ground state. That's the principal quantum number. Whole numbers starting at 1, going until we're out of the atom, basically. The second quantum number is the angular momentum quantum number. Now, the angular momentum quantum number is given by the letter L. This is a style choice for me, but L, I use a script L instead of a print L because my print lowercase l's look like 1s. And I don't want to get them confused. So you might see it listed as just, a lowercase l and not in script. That's okay. Again, this is a style choice that I use to help me differentiate between this quantum number and the number 1. With the angular momentum quantum number, What we are describing is the shape of the orbital, sometimes referred to as the subshell. The allowed values for L range from 0 to n-1. And those values of L correlate to particular shapes. So when L is 0, we are describing an orbital shape that is S, spherical. When L is equal to 1, we are describing a P-shaped subshell. When L is equal to 2, we are talking about a D subshell. When L is equal to 3, we're talking about an F subshell. And we can go further and further and further. The reason we stop here is because these 4 subshells are the ones that are the only ones that exist in the ground state. And I didn't show you pictures of F because the pictures of F get really, really complicated. But we understand that orbitals with the same values of N and L are in the same subshell. And if they're in the same subshell, they have the same energy. So we've taken the broad scope of all electrons, we've reduced it down to those that are just in this one energy shell, and now we've reduced it down to those that are just in this particular subshell. And all the orbitals in this subshell have the same shape, have the same energy. The next quantum number is the magnetic quantum number. The magnetic quantum number describes the orientation of the orbital in space. So we are getting down now to the specific orbital that an electron is in. The magnetic quantum number is constrained from values starting at -L and going through 0 to +L. And so this is what tells us how many orbitals are in that sublevel. So how did we know that the P sublevel had 3 different orbitals, 3 different orientations? Well, the quantum numbers told us so. Since L for the P orbital is 1, the possible values were -1, 0, and +1. That's 3 different orientations. That's how we knew that there were 3 different orbitals in that sublevel. For the D orbitals, L is equal to 2. So it's -2, -1, 0, 1, and 2. 5 different orientations, 5 orbitals in that sublevel. The last quantum number is the spin quantum number. This gets us to a specific electron. Each orbital is capable of holding 2 electrons. Those 2 electrons are either spin up, which means they have a spin quantum number of +1/2, or spin down and have a value of -1/2. It's one or the other. And the reason it's one or the other is due to a concept known as the Pauli exclusion principle, which states that every electron has to have a completely unique set of quantum numbers. And so I can't have both of them pointing up, because that would mean that both of these would have the same 4 quantum numbers. I can't have them both pointing down, because then that would mean that they'd have the same 4 quantum numbers. One has to be up, one has to be down, to give us the 2 different spin quantum numbers to satisfy the Pauli exclusion principle. right, so before we break for today, let's do a review question and then the final question. All right, so for the review question, knowing our constraints on N and L, which of these combinations are not allowed? And so just walking through this, what we have to understand, we can go through this systematically. N has to be a whole number. Are any of those not whole numbers for any of these 5 options? No, they're all whole numbers, so that works. Second thing, L has to be anything from 0 all the way up to N minus 1. N minus 1 defines that maximum boundary for L. So if I look at A, N is equal to 2 and L is equal to 0, that works. L can always be 0. N equals 5, L equals 3. Okay, well, 3 is not always an allowed value, but if N is equal to 5, the maximum value is 5 minus 1, so that's 4. So yeah, that works. L can be 3 in that energy level. Can N be 1 and L be 1? No. That's the one that's wrong. And the reason it's wrong is because in that first energy level, you can only have one sublevel. That sublevel is S. That describes a 1p orbital, and there are no p orbitals in the first energy level. For the other ones, we can apply similar logic. Fourth energy level, L can be 1. Third energy level, L can be 2 because that's N minus 1. All right. So last thing that we're going to do, we'll do this guided practice on Wednesday. That'll be kind of a good review and recap for the homework assignment. Homework assignment is a lot of questions like these. What quantum numbers are used? When are these allowed? When are they not allowed? What are the possibilities for these given situations? What do these orbitals look like? On your way out today, make sure that you answer this last question. And so on Wednesday, we'll finish up this discussion, just kind of wrapping up a little bit with quantum numbers. And then we'll get into the most relevant application of quantum numbers, where we start to describe where every electron is in an atom at the same time. It's called an electron configuration. And so that will be what we do on Wednesday. Have a great day.